Okay, so good afternoon, everyone. I have shared my screen. Hope you can see my screen. So today our topic of discussion will be Vertex cover decision problem, another standard NP hard or NP complete class problem. So let's start that topic. So what is a Vertex cover? So Vertex cover of a given graph G equal to V comma E is a subset of vertices, a subset, let's say S, of vertices in G, such that at least one endpoint of an edge of all edges of all edges are included in S. Okay. So, for example, we have we consider a bipartite graph. Okay, so consider this a bipartite graph. Uh, okay, it's a bipartite graph, and this is your x, and this is y. Okay, okay. So here we want to find out a possible subset of the vertices in G. So we have six vertices in G. Okay, 1, 2, 3, A, B, C, and we want to find a subset of this set of vertices capital V such that all the edges will be covered. At least one point, end point of each edge will be included. Okay, in that subset. So let's try to find one such vertex set. S equal to, let's say, uh, if I include 1, okay, so if I include 1, then this edge is covered. Okay, this edge is covered. My logic is, if you want to include a vertex, at least one endpoint of this edge must be included in that set S. So each edge will have two vertices. So at least one vertex you include in the subset. You can include both of them, 1 and A, but it is sufficient to include either 1 or A. So let's include 1. So this is covered. Next, let's say we want to next let's say 2. In that case, this is covered. Okay. Next, let's say 3. This is covered. Okay. You may not include vertex A because the edges which are connected to A, all of them are already covered. So you may not include A, so I am not including. But these two edges are still not covered, not yet considered, these and this. And to cover them, you know, these are covered. Okay, 1, 2, 3. How? So as I have included vertex 3, so the this edge is having one end point which is 3. So already that is included. That means this vertex is covered. Similarly, this edge. Similarly, this edge is also covered because one end point of this edge is 3. So we can find one such subset S of subset of V such that all the edges, at least one endpoint of all the edges are being covered. Right? So this S is here a possible vertex cover. Vertex cover. Okay, of G. Right. So we have S equal to 3 in this case. The size of the vertex cover is 3. The size of vertex cover is defined as the number of vertices in that vertex cover. In this case it is 3. Is the size of vertex cover S. Okay, fine. So the question is, S may be, as S is a subset of V, we may include all the 6 vertices in S. That is also a possible vertex cover. I mean, V itself is a vertex cover, the largest vertex cover. Okay. So what is our goal? Our goal is to sorry, excuse me. Hmm. So our goal is to find vertex cover of minimum size. So it's a minimization problem. Okay, so this is our goal. So in our example, what we have, that is, let's try to find out the minimum vertex. So the minimum vertex can be the above bipartite graph. The minimum vertex would be, A is equal to, okay, if I include A vertex, then this vertex, this edge and this edge, which are incident to the vertex A, all these 3 edges are covered at a single shot if I include the vertex A. I do not have to include 1, 2 and 3. Just consider vertex A. Similarly, if you consider now at this situation 3, the vertex 3. Okay, so if you include vertex 3, you know, this edge and this edge will be covered. That means all the edges are being covered. At least one end point of all the edges are here, A and 3. And we have found a vertex cover of size 2, which is less than this vertex cover. And you will figure out that this is a minimum vertex cover size 2. Okay, so this is our example. Okay, A and comma 3. And one possible logic you may find here, that is okay, so okay, let me draw this picture again. Let me draw this picture again here. Right, so here uh, what I do, okay, so just okay, right, so the degree of A is in this case 3, the degree of B is 1, here the degree of C equal to 1, degree of the vertex 3 is 3, and degree of 2 is 1, and degree of 1 is 1. So you target first the vertex which is having the maximum degree. Here it is A and the vertex 3, so you target them. Okay, so here what you can find, that is S equal to, okay, you target first 3. Okay, so then these are covered, these are covered, this is covered, this is covered, and also this is covered. Okay, so this is already done, vertex 3 is done. Next you target the next possible vertex which is having the next maximum degree. In this case it is A, so you go for A. Okay, you go for A, and you will see that this edge and these edges are covered, and hence on the edges are being covered. Okay, so in this way you can also find the minimum vertex. This will give you a minimum vertex. Okay, minimum vertex. Okay, according to the degree concept. Okay, now what we will do, if it is let's try to develop an algorithm to do this. Okay, so um, algorithm for vertex cover finding, algorithm for finding vertex cover. So we will be given a graph with vertex set V and edge set capital E. So let's say our graph G method. Right. G, where G is containing, not except this. So what you do here, the set n, V is a set of what is V is an array which are, you know, v1 comma v2 dot vn, where v1 comma v2 dot vn. So you copy all the vertices into the array, and then you sort v1 is to n, okay, in non order. Then for I equal to 1 to n, go for actually, let's say s equal to um, the phi is denotes null, okay, right, right. So here you do one thing, that s equal to s union v, and then you check here, then you check there, you uh, call a function, okay, h, find this function, there you pass vertex set h set e, okay, so it's left, right. So this function edge left, if there is any edge left to be, so if edge left, then you go for the next iteration, This is true, then you go for next iteration, edge left, true. You do not have to do here. Do false, then return. Return is. Okay. So end for. So this is the possible logic. This is the logic which we try to use over here to find out minimum vertex. This is for finding not. This is minimum vertex cover. Okay, minimization problem, and it is following order of n complexity, time complexity. Okay, so something here, edge left, you initially edge left means uh, you provide here an adjacency matrix capital A, the help of capital this. Okay, so you do one thing for I equal to 1 to n. Okay, okay, here you compute the adjacency matrix. Let's say A. Okay, so I'm not going for computing adjacency matrix. Let's say that this is already given. Okay, so you pass that adjacency matrix into the function is left, which will check that. So here you check. Okay, this could be some logic, so we can't say at this moment what can be the logic of this function, but we are interested on this. Okay, this is so which is the time complexity here n is equal to order of right. Okay, so it's fine, it's a good deterministic polynomial time algorithm, minimum vertex cover, which is a minimization problem. Okay, so this is fine. So taking this example, we find a minimum vertex cover 3a. Okay, now what is our problem statement in our context? That is, given a graph G equal to V comma E, we have to check whether that graph contains a vertex cover or not. Okay, minimum vertex cover or not. Okay, so the problem now is a minimum vertex cover, a vertex cover decision problem. So the problem statement is given a graph G equal to V comma E, we have to find a vertex cover given a, okay, yes, we can find a vertex cover. Obviously, for any graph we can find a vertex cover, but the problem statement in this case, given a graph G equal to V comma E, we have to find a vertex cover of size maximum k or at most k. Given a size V comma E and an integer k, we have to find a vertex cover, whether that graph contains a vertex cover of size at most k, then it's a good problem. And this problem we can derive today, uh, proof that this problem is an NP hard problem or NP concrete problem. Okay, so all the NP hard, all the NP hard problems which are uh, no, no, we are including a vertex into S set. Okay, right. So we are including a vertex. So V1, okay, sorry. So it is V1, it is Vi. Including a vertex, vertices are denoted like V1, V2, Vn are V1, V2, V3, right? So those vertices are being included into S. Okay, as soon as I have, there is some edge left in the graph. Okay, if all the edges are covered, I will stop. So given a graph G and an integer K, and we can prove that this problem is an NP hard problem, and an NP hard problem is an NP complete problem if that problem belongs to NP. Means if we can construct an algorithm which is non-deterministically polynomial time algorithm for that NP hard problem, then we can say that that NP hard problem is an NP complete problem. That right? So these are our definitions which we have already covered here. Okay. So next, what we go for output. So let's furthermore we have to prove that uh, DP is an NP hard problem. Okay, go for it. So okay. Okay, so let's take an example. Let's take an example. It will be better to relate. The proof is a very good proof. You know, uh, very. I mean, analytically, it has been proved. One. This is two, three, four. Right. Okay. So one, three, four, five, and the edges are connected like this. These one, two are connected. Five, four, and are connected. These and these are connected. One, these are connected. Right. So this is the graph. So here what we do. So uh, okay. We have a theorem. The theorem is uh, VCDP. Okay. The theorem is VCDP reduces to CDP. Okay. Oh, একটু হয়ে গেছে, সরি। Proving the reverse, right? Okay, so we want to treat that this is, this is your L1 and this is your problem L2. Okay, so if we can, so a problem L2 is NP hard if and only if L1 problem reduces to L2, given that L1 is already a known NP hard problem. Okay, that's why we want to target this theorem. Already we have a theorem and we will go for its proof that a click decision problem reduces to this vertex cover decision problem. If we can prove this, that means we can straightforward say that VCDP is an NP hard problem. So let's go for it, proving this theorem. Click decision problem. So let k be an integer problem instance, and small k, please note it down. So small k, and let be a vertex cover of G. Okay, vertex cover of G, um, vertex cover of G, that's fine, and vertex cover of G. Okay, right. So then, that is, we can say that, how can we write that A is equal to, so the vertex cover is supposed to cover all the edges, but we should have possible, possibly minimum number of vertices in S, so as to cover all the edges of the graph capital G. So A is equal to, the vertex set is getting changed, but the edge set is remaining same. So V dash, let's say V dash, comma E. Okay, and let capital K, okay, small c, let capital C, so let small c be a clique of size, do not know its size, so of, okay, let it be of size, um, okay, fine, so right. So what is the proposition here? That is, we claim that, we will say that, so we can construct, clique C of G only if and only if, okay, so before that what we have to do here, so we construct a graph G dash, okay, such that G dash contains a vertex cover, okay, of size at most n minus k. Okay, so initially we assume that S be a vertex cover, V dash comma E, C be a clique of G. I don't know its size. We will eventually find out the size of that clique. Okay, then we try to construct a graph G dash it will help us, this construction g dash, such that g dash contains a vertex cover of size at most n minus k. Then we can construct a, we can say that, or okay, we can say that a clique, that there exists a clique of G, okay, if and only if G dash contains a vertex cover of size at most n minus k. There exists a clique C of G of size at least k, there exists a clique C in G, okay, in G তাহলে পরে লিখতে হবে. So I hope you are understanding. So right, okay, so we can say that there exists a clique C of size at least k. So the clique is of size at least k in G if and only if G dash contains a vertex cover of size at most n minus k. So this is our claim. We will prove this claim. If we can prove this claim, then we can prove that theorem, and if we can prove that theorem, we can prove that VCTP is a NP hard top. Okay, fine. So let's go for the construction of this G dash graph. So the G dash is defined as follows, that G dash will be equal to already 126. Okay, fine. So G dash equal to comma E dash, same vertices. So G dash of G, so this is a graph, this is a special graph, I will name it later. So G dash of G is defined as follows. So you will take same vertices, all the vertices of capital G. That's why the vertex set is not changing, but the edge set is changing, E dash. Okay, how? So G dash becomes equal to V comma E dash, such that E dash equals to the set of all those edges U comma V, okay, U comma V belongs to V. These are vertices from V, but and U comma V edge does not belongs to E. Okay, so this is the definition of the construction of G dash. So this G dash, here is called the complement graph of G. This is the complement of graph G. So as per our example, we can construct the G dash, so let's try to construct the G dash complement graph. Vertex 1. So all the vertices have to be considered. Now edges, okay, name the vertices. This is 1, this is 2, 3, this is 4, 5. So this edge was connected 1, 2. So this will not be in the E dash. Okay. So 1, 3, 1, 5 was not an edge in E, so it becomes an edge in G dash. So 1, 4 was connected 5, 4. So 1, 3 will be an edge, 5, 3 will be an edge. Okay. Any other? 2, 4 is an edge. 2, 4 is an edge. I think it's complete. Okay. And for your convenience, just let me write here the degrees. The degree of 1 is 2. In this case, 3. This is 2, and this is 3, and this is 2. Okay. So I will give you one question in the quiz that will relate that will give you a relationship between a degree of any vertex in the complement graph with the degree of any vertex in the original graph G. Okay, so this is 1, this is 2, this is 2, and this is 1, right? So these are the degrees. Okay, so this is complete. So this is the meaning of the complement of graph of G. Okay, this is how we will construct. Okay, and this G dash contains a vertex cover, okay, of size at most n minus k. Okay. Then we are almost about to the proof. As C is a clique of size mod C, we do not know its size, so mod C. As C is a clique of size, C is a complete subgraph of mod C means, of size mod C denotes the number of vertices. C is a complete subgraph of eto vertices. Okay. That is uh, all vertices are adjacent or connected. Okay, fine, connected to each other. Each other in G. So C is a clique of G. Please try to concentrate here. This is the vital moment. So C is a clique of size mod C, and C is a clique of graph G, right? So all the mod C vertices are connected to each other in graph G. So immediately we can say that the remaining total number of vertices is n. I just forgot to mention you that n was used, but it is not anywhere mentioned. Okay, here n minus k, where mod v is equal to n. That is, we have total n number of vertices in the graph G. Okay, so the remaining n minus mod C vertices in G dash, okay, are not connected to each other. That means uh, right. So n minus right. So this n, okay, are not connected to each other. So okay, let uh, track one clause. The G contains, okay, this is a clause, given clause. There is 2, okay, uh, and click where it is given, right. So okay, then it becomes 1. So okay, so GDS is not are not connected to each other. GDS are not connected. So the n minus k vertices in G dash cover cover all the edges, uh, all the G dash. So n minus k number of vertices have to cover all the edges, e dash number of edges. Okay. So and we are given that it will contain a vertex cover. So is the vertex cover of n minus k size, because because S is a vertex cover of size n, okay, of size at most n minus k. Okay, right. So next what we can write, that is um, is equal to, what is S? Have we defined S? We have to establish a relation, right? S equal to V dash comma E, right? So this is our 1 and this is your 2, clause number 2. Okay. So from 1, so from clause 1, we can say that the vertex cover contains, uh, you know, V dash number of vertices. Okay. So V dash is less than or equal to, V dash is less than or equal to, less than or equal to, less than or equal to, S is a vertex cover of size at most n minus k, n minus k. Okay. So the n minus k vertices in G dash cover all the E dash edges in G dash. Okay, so we got this information. S is a vertex cover of size n at most n minus k, and V dash is the number of vertices in it S. That means the number of vertices V dash is less than or equal to n minus k. So we can write like this. Okay, so, from the information 1. And next, what in terms of click, what we have here, the click, the n minus mod c vertices in G dash are not connected to each other. Okay, So in the next line, what we can write, n minus mod c. In the next line we can say that n minus mod c is, less than or equal to less than or equal to uh, from, yes, it is. Okay, hence we can write that. Okay, mod c less than equal to this n minus k. Next line, what we can say, that is is less than or equal to minus k. So in the next line we have mod c greater than equal to. Okay, that means we have shown that the click C in G must be of size. So we can, that means, yes, we can construct, so the graph G contains a click of size A if and only if the complement graph G dash of G has vertex cover vertex cover is vertex cover is of size at most n minus k. Okay, so this is proved. So this is the theorem. This is the not the theorem. This is the claim. So this is the proof of claim. So claim, hence the theorem is proved. So hence, so finding, that means, is there any click in the graph? Yes, there is a click in the graph. How? Because the complement graph is containing a vertex cover of size at most n minus k, which is the claim. Okay, so hence with the problem CDP problem, hence CDP problem reduces to vertex cover decision problem. Okay, we have already we know that satisfiability reduces to CDP. Okay, and CDP reduces to VCTP. So in the next line we can say that satisfiability reduces to CDP as transitive. Okay, so in the next line, what we can say, that VCTP is an hard problem. Proved. Okay, that's all. And next, what we can go for, so as CDP is a is an NP problem, means uh, CDP has polytime deterministic algorithm. Okay. So we can have a non-deterministic polytime algorithm for VCTP, and hence VCTP is an NP problem. Okay. Because CDP reduces to VCTP, so that means CDP is polynomial. We have an algorithm polynomial time non-deterministic for CDP. That means obviously this is having a non-deterministic polynomial time algorithm. Okay, so it's an NP problem. Okay, so hence uh, complete problem. The NP hard problems which are NP are also NP complete problem. Okay. Okay. So VCDP can have a non-deterministic, polynomial right. Okay. Because probably I have shown you the graph. If I have not shown you, just let me show you this thing. Okay. So this is and this is P, and the portion which is the intersection of NP hard and NP. Okay, so this portion, you know, okay, so this portion is NP. So the NP hard problems which are also NP are actually NP complete. Okay, that's why VCTP is an NP complete problem. Okay, so this is the relationship, believed relationship between NP completed. We have derived today, proved today one problem, very standard problem, which is Vertex cover decision problem as an NP hard problem and also as an NP complete problem. Okay, so if you have any question, you can ask me. We are done and we can wrap up. Okay. So I hope no question. We can stop the recording.